Slide आगे ले जाओ. Students, are you listening to me? Am I audible?
Yes, ma'am.
Yes, ma'am.
Sorry for the interruption. Some internet problem was there. So I'll continue. So we are talking about the hydroxides. And just now I have told you that the hydroxides of this group elements are in the form, they form this type of hydroxide, XOH whole 3 type hydroxide. Boron forms BOH whole 3 type of hydroxide, which is acidic in nature. Aluminum and gallium hydroxides are amphoteric in nature. Indium and thallium hydroxides are basic in nature. So just we see that as we move from boron to thallium, the hydroxides of these, from boron to thallium, the basic strength of hydroxide increases. That means from top to bottom, if we talk of the hydroxide, their basic character increases. That means thallium hydroxide is most basic in nature. Any doubt? Now, there is a very important question often asked that if we aluminum halides, we are talking of aluminum halides, AlCl3. It is often asked when AlCl3 is added to water, it ionizes, means it dissociates into Al3 plus ion and 3Cl minus. Why? Aluminium is ionic. AlCl3 is ionic in aqueous, but it is covalent in non-aqueous solution. Why? The reason is this peculiar nature. This reason is because of its hydration energy. We all know that aluminium, if we want to convert aluminium to from Al to Al3 plus ion, that means we have to remove 1 electron, 2 electron, and 3 electron. That means ionization enthalpy, first, second, and third. All total, we require 5137 kilojoule per mole. This much energy is required. It's a very big amount. So in non-aqueous solution, when we are talking of non-aqueous medium, this much energy is not available. That's why it is covalent in nature. But when we add it in water, what will happen? The hydration enthalpy is there. So hydration energy for Al3 plus ion is minus this much, 460. This is the value for this hydration enthalpy. This much energy is released. Now this energy plus the hydration energy of chlorine together make an amount this much, which is more than 5137 kilojoule. So this energy, that means the hydration energy of aluminium, makes it possible that it can ionize. This exceeds the ionization energy, so AlCl3 ionizes. So the question is, AlCl3 ionizes in aqueous. Why? The answer will be, in short, due to high hydration energy. Any doubt? If the question is AlCl3 ionizes in aqueous, why? So your answer will be due to high hydration enthalpy of aluminium. Are you getting it?
Yes, ma'am.
Yes.
Now the halides of the compound. One halide, aluminum halide, I have just discussed the hydration enthalpy. Now we are talking, we have discussed the oxides, the hydroxides. Now we will be discussing the halides of the elements of this group 13. So they will form the halides of the type BX3. That means, EX3. EX3 means boron. Suppose X is chlorine, then BCl3, then AlCl3. उसके बाद आप चले जाए गैलियम में GaCl3. Then we go to indium, InCl3, then thallium, TlCl3. So this type of halides are exhibiting. That means we are getting this type of halides. BCl3 to TlCl3, the ionic nature increases. As we move from BCl3 to TlCl3, their ionic nature increases because as we move down the group, we all know that metallic character is increased. So in case of BCl3, we are talking boron is bonded to 3-chlorine. Boron is bonded to 3-chlorine. That means it is acting like a Lewis acid. Do you agree? Do you agree it is behaving like a Lewis acid? Because one p orbital is empty. One p orbital is empty. Octet is not complete. Only 1, 2, and 3. 3 pairs of electrons are around the boron. 1, 2, and 3 pair of electrons. That means 6 electrons are there around the boron. That means this octet is not complete. It is able to accept a pair of electron from any donor, Lewis basis. So it can accept a pair of electron. That's why it is behaving like a Lewis acid. So halides of group 13, they behave like a Lewis acids. Okay. And they can gain a pair of electron from Lewis bases like ammonia, and they can form a coordinate compound like this. Now, AlCl3 achieves stability by forming a dimer. That means, agar we are talking of AlCl3, again it is behaving like a Lewis acid. Its octet is not complete. So it is ready to accept a pair of electrons. So what happens? The other AlCl3 molecule, 2 molecules of AlCl3 are there. This Al and this 3Cl, and this Al with this 3Cl. So 2 molecules AlCl3 dimerizes. How they dimerizes? The chlorine atom is having lone pair, which it can easily donate to the aluminum of first molecule. And the chlorine of first molecule can donate its electron to the aluminum of the second molecule. So here one bond is there, coordinate bond, that is this chlorine is donating a lone pair to aluminum, and here this chlorine is donating a pair to aluminum. And this way their octet get completed, they dimerizes. Such type of bond is known as bridge bonding. This is bridge bond. Okay. Often this question, this is very important question. Why AlCl3 dimerizes? So your answer will be to achieve the stability, they dimerize. Am I clear to this point? Or you want me to explain this once again, the bridge bond? Anybody in the class? Okay. Now a very important point to discuss, the trihalides of boron. The trihalides of boron we are talking, so they will form of the type, suppose it is bonding with fluorine, BF3 type, chlorine, BCl3 type, bromine, BBr3 type, and iodine, Bi3. So these are the trihalides of boron. And just now I have explained that they behave like a Lewis acid because they are electron deficient. Only 6 pair of electrons are present around the in the valence cell of the central atom boron. So they behave like Lewis acid. So children, can you explain me which of or you can arrange the halides of boron in increasing order of their Lewis acid strength, acidic strength, which will be most acidic in nature? Can you guess? Can you guess, anybody?
BF.
BF3. Generally, students.
BI3, then
Oh,
BR3, then
very good.
BCl3, then BF.
Very good. Who is that boy? Can you give me your name?
Pratik, ma'am.
Very good. Pratik of section A.
B.
B section. Very good. So this is most acidic in nature. Why? Because a reason is there. Just in the next slide, I will be explaining the back bonding. Actually, in one shot, you look that fluorine is most electronegative. So this will be This will be most acidic in nature, but this is not like that. In the next slide, I will be explaining the back bonding. Okay. Just to go to the next slide. Okay. Now what happens? If we are talking of the acidic strength is in the order BF3 is less than BCl3 is less than BBr3 is less than Bi3. That means Bi3 is most acidic in nature. This is again a very important, a very good question often asked. So acidic strength of the halides, different halides of boron. So Bi3 is most acidic. Now what is the reason? The reason is that boron is bonded to three halogen. Suppose BF3 or BCl3 or BBr3 or Bi3, whatever is there. Now, it is having the fourth p orbital. One of the p orbital is vacant because its octet is not complete. So one of the p orbital is vacant and it is ready to accept a lone pair from anywhere. So it can easily accept a lone pair. So it is behaving like a Lewis acid. Now what happens when it is bonded to fluorine? When it is bonded to fluorine, then what will happen? The 2p empty orbital of boron and the 2p filled orbital of fluorine. That means both the orbitals are of same size and almost same size. So the back bonding, that means the fluorine can donate its lone pair to the empty orbital of boron. Fluorine can easily donate its lone pair to the empty orbital of boron because of almost similar size. 2p of boron and 2p of fluorine. But as we move from fluorine to chlorine, it is not 2p, it is now 3p. We moved from chlorine to bromine, it is not 2p, 3p, rather it is 4p. And if we move to iodine, then the p orbital of iodine will be 5p. So 2p back bonding can easily form because of their similar size. Similar size overlapping, sidewise overlapping can exist. And this bond, the p-pi bond will be stable. But as we are moving away and away, that means we are moving to iodine, the involvement of 5p will be there. That means 2p of boron will be overlapping with 5p of iodine. So 2p, 5p overlapping will not be successful or not be very stable. Just you see, in fluorine and boron, the size